Good evening, Balamurugan. How are you? Okay, good. Ashish, what about you?
I'm fine.
Okay. So, how's the course going? Like, are you
Yes,
enjoying this subject or not?
yes.
Okay, and what about the problems?
Yeah, we I'm solving the numericals which we have received on assignments,
Okay,
and it's yes.
that's good. Okay, I'm still waiting for few minutes. Maybe after 6:10 we will start the discussion. Are you facing any kind of difficulty in solving the numericals? Like, if any, with your support, assessment are easy for me. Okay.
Yeah, it's easy,
Thank
no
you,
issue.
Balamurugan. Thank you. Good evening. Wait a minute. Someone wants to join. Okay.
Good evening, Prabhat. Good evening.
Uh, Good evening. Good evening. Uh, can you introduce yourself? Like, it will be better if
Sure.
I know you.
Sure. I'm Manikumari Nagapan. I'm working as Professor of Civil Engineering in Annamalai University
Okay. Yeah,
for
that's
the
good.
past 30 years.
Okay. Okay, that's good.
I'm my area of specialization is water resource engineering. So I've handled few subjects. So I just want to strengthen my
Yeah,
knowledge.
that's good.
Thank you.
Yeah.
Thank you.
I also want to listen from Manikanta. Can you introduce yourself? Like, this is the
Sir,
first time you
good
are.
evening,
Yeah.
good evening, sir. Myself, Manikanta, I am from the Goodwaller Engineering College. I am now studying a BTech prod year.
Okay.
Uh, I completed NPTEL certificate from Geometric Design of Highway. Now I choose the engineering hydrology for my furtherly improve my grade in the NPTEL. Sir.
Okay. Okay.
Uh,
Okay. That's good. So it's a part
yes,
of your BTech curriculum, right? certificate?
Yes, sir. I recently completed the give the GATE exam. Regarding that, also I gained some knowledge from engineering hydrology subject.
Yeah.
For that reason, I choose that subject.
Okay, that's good.
Thank you, sir.
Nice to know this. Yeah.
One question, please. What is it? I mean, we have one session from 6 to 8 and the other from 7 to 9.
Right.
So
Yes.
two scholars are handling. Is it right?
Yeah. Yes.
Okay. Last week I was little late at 6:20 or 6:25. I was asking permission to enter into your session. Not last week, the week before that, I think. Uh,
Okay. Okay.
but because I was little late, I wasn't able to join the
Yeah.
session. Then I attended the next one, 7 to 9.
Okay. Actually, sorry for the inconvenience. Actually,
No, no, it's
whenever
okay.
I'm looking at the presentable screen, I'm not
Okay,
able
okay.
to quantify that whether
No, no,
we.
no problem, no problem.
Yeah.
It's always best we join in time.
Yeah.
Thank you, thank you.
Okay.
So both are aimed with the same purpose. Am I right?
Yeah. Yes. 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 Of
Okay.
course.
Thank you, thank you.
Okay. Now I'm starting the session. Let me share my screen. Ashish, can you let me know that this screen is visible to you?
Yeah, it's visible.
Okay, good. Okay, welcome to this session. So today we are going to see the assignment on Engineering Hydrology Part 5 regarding NPTEL course. So before going to this, some of you are new to this session. So myself, Prabhat Dwivedi, I am currently working as a PMRF Research Fellow in the Department of Hydrology, IIT Roorkee. So today we are going to discuss brief concepts and the numerical problems which are associated to subsurface water. We will be looking at how the water from atmosphere is getting infiltrated in the subsurface part and how is it moving beneath the surface, beneath the subsurface. Next, we will be looking into the infiltration process, like how we can compute what are the different methods related to this. Then yes, of course, there may be certain instruments which will be helping us to quantify the infiltration magnitude and the variation with the time. We'll be looking at some of the problems related to infiltration which are based on empirical equation. We will be also touching the concepts, maybe principle on which these green Ampt equation rely on. So in general, I want to know what you understand by subsurface flow. Firstly, I want to listen from you, then I will go in the details, and then further we will be discussing the question and answer session. So can anyone tell me that what you understand by subsurface flow and how is it actually occurring in any kind of watershed? Ashish?
Yeah, subsurface flow is the flow of water below the ground surface
Yes.
due to the intermolecular forces, and it's following due to the gradient also.
Yeah. So one point is right. You are correct that there will be a gradient. Yes, of course, there may be a gradient. Then another major aspect will be a gravity flow, right? Where the gravity force is acting. So in most of the cases, subsurface flow is basically divided in two major categories. One will be an part which related to unconfined aquifer and other will be a confined aquifer. Okay, and in both the cases, yes, gradient will be playing a major role. Then other than this, gravity force will be acting, and then other aspect is also atmospheric pressure, we can say. Okay, so now from the first picture you can see it is this picture is showing that there could be some atmospheric precipitation which is falling in the region, and then subsequently infiltration is going on. So how infiltration is going on? So whatever the surface water which is falling over the land, with the passes of time, this rainfall or maybe a precipitation, it is passing through the soil pores. Okay, there may be a interconnecting soil voids, this subsurface voids may be there, and then water is passing through that region. Okay, in parallel you can also see part of the water can also flow as a runoff, that will be counted as overland flow, and it is finally meeting into the stream. If we divide infiltration into based on the depth, okay, so this infiltration may be divided in two major parts. One could be an unsaturated region. You can see from this area this particular highlighted block, that this could be an unsaturated region, okay, and the same time this could be a saturated region. Why I am calling this? Because in case of unsaturated, there is little possibility that water is just coming water is just accumulated as a part of groundwater flow. So here you will be seeing a little amount of moisture between the soil pores, but at the same time, if you count the region below the water table, this is the water table, okay, here the groundwater flow is actually occurring. So below the region of water table, we are counting it as groundwater flow. Now in the second picture you can have some better idea that this unsaturated region is also divided into two major parts. Like from the saturated region, water is available, yes, of course, but there could be a capillary action, like because of the surface tension, there could be a capillary action from which negative pressure is causing uplift movement of water in like up to a certain depth only, okay. Now I am moving ahead to explore questions as well as the basic theoretical concepts related to these topics. So the question coming first is, the flow towards the stream from unsaturated zone beneath the ground is termed as. So just I mentioned about the saturated zone. So it is asking that what could be the possible parameter which is causing a flow from the saturated zone and meeting into a stream. So anyone can answer.
It's interflow.
Base flow, sir. Base flow.
What?
Interflow, the number one.
Okay, Ashish, you are saying interflow. Okay. Other people?
Base flow, sir.
Okay, base flow. Okay. Anyone else? Ashish, you can also tell me the replies from Bala Murugan.
Yeah, he said the base flow, I think.
Okay, base flow. Yeah. So yes, Ashish, it will be a base flow only.
Okay.
So we
Base
will be
flow.
looking.
I think it's base flow, sir.
Yes, right, ma'am. So yes, of course, it will be a base flow, because whenever we are talking about the interflow, so that is a part of the groundwater flow only, and it is also generated because of the delayed movement of water. So definitely whatever the precipitation is falling in the region, it is getting it is moving, or maybe I can say it is getting infiltrated to a greater depth, and then it is getting accumulated and finally causing a groundwater flow, and which is meeting at a I can say a stream, okay. So it will be called as a interflow, I guess, interflow, okay. So in the explanation you can see there is a water table. Now base flow is causing because of the saturated region of subsurface, but if I consider the above part, that is unsaturated one, so here interflow process is dominating. So from this explanation you can see within the unsaturated zone there will be a flow towards a stream, okay, and at the same time if I am talking about the saturated zone, so water movement is dominating and causing a groundwater flow towards a stream, so it will be called as a base flow. But in the previous case, if I am considering an unsaturated zone, so interflow process will be dominating here. Moving ahead, we can also see some of the explanation. So interflow is the lateral movement of water in an unsaturated zone. That is returning as a surface into a stream, in the surface water. It is returning. But in the case of base flow, it is just a display of delayed flow. Okay. Now coming to the question, which of the following equation is not used for infiltration capacity? So firstly, I want to know what you understand by the infiltration capacity. There could be certain kind of land surface. Rainfall is falling in the region. There is subsurface strata. Now this there will be a soil porous media. I will say that is a soil. So connecting voids will be there. So if I am talking about the infiltration capacity, so you can say that the rate at which infiltration process is dominating in the subsurface soil. Okay. So here it is asking that what are the estimation methods that are available for quantifying the infiltration capacity. Anyone can answer?
Yeah, it's Penman equation.
Penman's equation.
Yes, right.
NPTEL.
Okay, so Penman equation, can you further tell me that this equation, where we are
Gives
using this equation?
evapotranspiration.
Yes, yes,
Evaporation or evapotranspiration.
Right, yeah. So yes, of course. So Penman equation we are using for computing the ET in the region. So here Phillips equation, Horton's equation, as well as the Green-Ampt equation, these methods have different parameters, maybe different input data that we have to give, and then subsequently we are getting the infiltration capacity. So for your information, I have just added slide which are describing that this Horton equation, then Horton equation, they are the part of empirical equation. At the same time, Phillips equation and Green-Ampt, they are the theoretical equations. And you can also see, you may be knowing whatever the general formula is mentioned for different empirical equation. You might be knowing this from your lectures. Coming to the next question. So dash is the responsible for flow of water in an unsaturated media. So yes, this is related to, yes, so this is related to a kind of forces which are acting in the subsurface zone and then subsequently causing a flow. So what are they? List out them.
Suction head and datum head.
Okay, suction head and datum head, right? Another one will be, can you guess another option? Like there may be multiple option as well. Okay, so yes, of course, if you are talking about the unsaturated zone, so here only the suction head and datum head will be dominating. But yes, if I talk about a flow in unsaturated zone, in the subsurface zone, then velocity gradient will also be accounted. Not the velocity gradient, it will be a velocity head. Okay.
Well, yeah.
Yes.
Yeah.
But in case of unsaturated zone, we know that groundwater flow is not dominating in this zone, right? Saturated medium is the only zone where groundwater flow exists, and whenever the groundwater flow will be there, it will be having a small velocity Okay, are you getting? If I draw a picture this is a subsurface zone. Then if I say that this is the water level, water table, so this region above the water table, just above the water table, it will be having unsaturated media. Maybe you can ignore some of the part because here capillary action will be dominating. Yes, of course, because of the negative head. So, but if we go out of this region, out of the capillary action region, then we will be having an unsaturated medium where you cannot find any kind of groundwater movement. Okay, but if we are talking about the water region beneath the water table, then you will call it as saturated region. So this is a saturated region. So definitely here the groundwater movement will be there, and because of this there may be a change in velocity gradient also, and that is causing a velocity head. You can see from the explanation, total energy H consists of the three components in an unsaturated zone in subsurface flow. But you can note it down here that this velocity head that I am talking about, it will be nearly zero, okay, because groundwater flow is not here. So definitely the final parameters which are causing the flow here is suction head and datum head. Moving to the next question, the moisture content in which zone is the moisture content in which the zone is above field capacity but below the saturation. So it is asking about a moisture variation with the depth. Okay, so with the depth, how the moisture is varying. Are you getting, Ashish?
Yes, yes, yes.
It is asking about the moisture variation with the depth. So have you studied the variation of moisture content with respect to depth below the ground? You might be knowing the profile like this. Do you remember this profile?
Yes, yes, yes.
So name them, that what we are calling this region. There we are calling this region like as first. You should
Transition, I think transition zone.
This is not a transition zone. First one, it is not.
Saturated zone, I think, right?
Yes, right. So this is a saturated zone. Why we are calling it as a saturated zone? Because once, if a rainfall is falling in the region, then within, I'm just saying t equal to 5 seconds. Okay.
Yeah.
So here you will be seeing that whatever the infiltrated water is there, it is moving up to this much depth. Let's say it is D1. But as the time passes on, this infiltrated water will be resisted by a front. Front in the sense what? There will be a dry front, okay, where the soil is not saturated, like it is not having any kind of moisture. So yes, it is not moving. Now there will be a change. There may be a change in the moisture content. So once it passes through the saturated zone, what would be the next zone you are knowing there?
Transition zone.
Yes, right. So transition zone will be there. Now note it down that this theta, whatever the theta is mentioned, this is the actually moisture content. So moisture content is directly proportional, or you can say it is dependent, not directly proportional. It is dependent dependent on void ratio. Do you agree with me? Moisture content is dependent on void ratio. So if I am saying that theta is 0 at certain case, like from the explanation you can see, I just added for the reference only. Firstly, you can see that how the porosity is defined. So it is just a volume of void divided by total volume of soil sample. And how we are defining the moisture content, so it is just a ratio of volume of water to the total volume of sample available. So what I'm just saying that initially the soil is dry. If soil is dry, then definitely theta is getting 0. Okay, so water has just started infiltrating. Okay, and the condition will be what? You are getting the top surface as void ratio is what? That is eta. It is equivalent to eta. As we are moving further down, then we are seeing that the subsurface soil is getting a moisture now, and it start coming in the wet zone. So here you will see a word wetting front. So because of that, why it is called a wetting front? Because of this front, we can differentiate between the dry soil as well as the wet soil. Okay. Now I am moving ahead. If the rainfall intensity exceeds the infiltration rate, infiltration will be equal to. So firstly, let me know what do you understand by rainfall intensity. What is rainfall intensity?
The rate at which precipitation occurs.
Yes, right. So it's a rainfall depth with respect to time. Now it is talking about rainfall intensity in comparison to infiltration rate. So yes, firstly I want to mention that if I am having 1 meter cube of porous soil media, if I am having, it can only withhold certain amount of water only. Beyond that we can't say that, yes, because if I assume that in total 10 meter cube of volume, 10 meter cube of rainfall is falling in the region. Okay, rainfall, why I'm just talking in the volume, because yes, rainfall depth we will be knowing, right? Rainfall depth we will be knowing. Let's say for an example, 6 centimeter of rainfall is falling, and I'm also knowing that what is the area of catchment. So I will be multiplying this depth with the area of catchment, so I will be getting the rainfall volume, that how much water have been accumulated in this particular region. Now I'm just talking about this subsurface zone. So I'm just saying that this surface zone has volume of only about 1 meter cube. This can store only 1 meter cube of water. But what will happen if I'm just saying that whatever the rain has fallen in the region, it is accounting 10 meter cube of volume. Will it hold this much amount of water here?
No.
Yes,
it can't.
It will not hold. Yes, right. So just to add this is just for the reference. It is asking this similar process that I'm just discussing now. That rainfall intensity exceeds the infiltration rate, then what could be the infiltration we are calling it as? So definitely
Potential.
Yes,
Potential infiltration.
maximum infiltration which can be stored in this particular volume.
Yes.
So it will be called as potential infiltration. So for your information, I just added the things. If I am calling it rainfall intensity as I, and this I is exceeding the infiltration rate, so we are saying that actual infiltration is equivalent to potential infiltration, like how much maximum water it can withhold. From the definition, this lines you can see what is meant by the potential infiltration. So this is the maximum amount of infiltration that can be occur at a given point of time. Moving ahead, interception losses. What do you understand by the interception losses, right? And then again, I'm just adding to this that why these interception losses are existing in our water cycle.
Before rain, rain falls on any medium, whatever projection like roof or trees, canopy,
Yeah.
the water which is caught by such structures is referred as interception. Am I right?
Yeah, right. So whenever the precipitation exists in the region, leaves are there. Definitely everywhere. If there is this interception losses basically depends on land use, land pattern, right? If I'm just saying that forest cover in the region is very high, then definitely there are more chances that out of 10 centimeter of rainfall or storm that is about to fall in the region, maybe accounted only 2 centimeter of rainfall in the ground surface, because it is possible that if there is a dense forest, then there is a possibility that 8 centimeter of rainfall can be intercepted by these by the leaves of these trees or maybe small plants. So yes, of course, it is just causing a interception in the movement of rainfall, right? Now if I'm just considering that this is a leaf, now drops are here. Now there is a more possibility that how this water could be lost. Can you guess what could be the process where this water can be lost from these leaves?
Transpiration.
Yes, that is a transpiration, but
Evaporation as well. Evaporation
yes,
and transpiration.
of course. So ma'am, here I just want to add one more thing. If I'm talking about this transpiration process, then you should be clear with the mind that whatever the water is moving out, it is it is within the leaves, like whatever the moisture have been stored in the leaves itself, that is causing a transpiration loss. Okay, ma'am, are you clear with this?
Yeah.
Yes. So leaves, definitely leaves will be carrying its own moisture. They may be extracting that moisture from the soil. Okay, and this moisture
I
will
think
be
that water lost by transpiration is coming from below, right? Not.
yes,
I think transpiration loss cannot be taken into account with interception loss, right?
right,
I was
right.
wrong, I
Yes,
think.
yes. Evaporation only will be the point that is accounting interception loss, because we are just like concerned with the water which is lying over the leaves, like whatever the rainfall have been fallen in the region, it is getting obstructed by the leaves. Now these drops are lying over the surface of these leaves, and once the heat energy is falling in the region, these drops have a possibility to get evaporated directly. But if I account the moisture which is moving within the leaves, then you can say that transpiration loss is also accounted. Okay, for accounting the transpiration loss, we have one terminology, that consumptive use of water. For that purpose we come up with that word, consumptive use, like how much amount of water we have to provide in order to compensate or compromise with the transpiration losses, because that consumptive use is basically have more importance when we are designing the canal. Okay, we are transferring the water from the reservoir to final agricultural area. So based on the transpiration losses, we are computing the consumptive use of water. So here the answer is it is mainly a evaporation loss. Okay. Now you can see whenever the rain is falling in the region, some part of the rain, it could be stored in the vegetation. Like vegetation is mean that those water drops are intercepted by the leaves. They are laying on the surface. Other loss could be sorry, not a loss, but yes, part of the rain will be contributing to a surface runoff, and the remaining part of the rain, it may be going as a infiltration. Now what are those region where this infiltrated water could be stored? So yes, it could be stored within the soil void, this porous voids which are there. So it will be stored at a soil moisture. Then yes, of course, further if we go, then that will be counted as an unsaturated flow. And then again, if it is going further deeper, then it will be meeting into a water table and contributing as a saturated flow. Now coming to the next question. The infiltration measured using the double ring infiltrometer is more accurate than that of the single ring infiltrometer. It is asking about the region.
B is correct, I think.
Which one?
B, second one.
Okay. Lateral spreading of infiltrated water will be only there at the outer ring. Why you are calling this? Like, can you tell me the reason?
Because for the double ring infiltrometer, we use two rings. One is inside and one is outside.
Right.
And so in
What
order
is the purpose of using
to
outer ring, and what is the purpose of using inner ring?
the purpose is that basically we want to make the 1D one dimensional steady flow.
Yes.
That's why we want to reduce the lateral flow of the water.
Right. You are right. So whenever we are having a double ring infiltrometer, so I am just talking about its this picture was about the cross sectional. I am just talking about the vertical variation. So yes, if I am just considering a single ring infiltrometer, so whatever the water we are giving into this, it may have a possibility that this water could go laterally, right? And we are not able to quantify, we are not able to clearly determine that yes, in this region, in this particular area, how much water have been infiltrated. We can't say, because already water have been lost in the form of lateral movement. So what researcher come up with, so they have firstly taken a single ring and then added other concentric ring. So just to avoid the lateral movement of water and causing it as 1D movement. Now the only water is moving as a 1D, because here what will happen, there will be a front will be there. Okay, front like front in the sense what, dry and wet front will be generated here. You will be seeing that whatever the soil particles are here, they will be getting saturated and they are forming a wet front now, and remaining this region, it will be remaining still as a there may be a little possibility that water is moving,
Will not move in the horizontal direction.
yes, right, exactly. So I'm moving ahead. So this picture is for your reference. So yes, of course, our target is to determine 1D flow, but in the case of single, sorry for the confusion, you can correct it. It is a single ring infiltrometer. Okay, so here we are not able to quantify 1D flow, but when we are using the double ring infiltrometer, we are able to quantify that, because we are able to prevent lateral movement of water. Coming to the next question, Green and Ampt theory proposed for infiltration capacity based on, so it is asking about the principle, that on what principle Green and Ampt theory have been designed.
Continuity equation.
Okay.
Yeah, the answer is.
Of course, if we are saying that continuity equation, then definitely this continuity equation cannot be accounted alone, because yes, of course, whatever the this entire infiltration capacity model is basically derived from Reynolds transport theorem, right? So this Reynolds transport theorem accounts both the principle, like continuity equation as well as the momentum equation. So momentum conservation will also be there, and this continuity equation will also be valid here. After solving the continuity equation, we are coming up to the Darcy law. Okay, we are finally getting the Darcy law. This Darcy law is basically this is applicable when we are having any kind of, we are assuming that whatever the groundwater flow is there, it is having a laminar flow. So this entire Darcy law is basically applicable for laminar kind of flow, and here groundwater can be considered as a laminar, because it is having very slow velocity, very low velocity. So here you can see that this Green-Ampt equation is based on the continuity equation as well as the momentum equation. When we are trying to go through continuity equation, so we are dealing with the parameters like moisture content, and then if we are talking about the momentum equation, we are dealing with the Darcy law. So whatever the question it was mentioned, Green and Ampt proposed a model for infiltration capacity based on, so here momentum equation is not mentioned, so we cannot alone say that fourth option is correct, but yes, of course, Darcy law is the major deriving force here. Okay. Hello.
Okay, got it.
Yeah.
Thank you.
Now let's do some numericals. Okay, so here there is one question. The observation obtained from infiltrometer experiments are given below. So when we are doing the infiltration test in the field, what we are actually doing, we are giving certain amount of water in the ring, and we are counting that how the with what time this water is moving beneath the soil, like how this water is getting infiltrated with the time. So in the field we got the values in the time as well as the cumulative volume of water added in centimeter cube. Now it is asking about the constant infiltration rate. So constant infiltration rate in the sense, we let's suppose we started adding the certain amount of water. Initially, whatever the soil present here in the region, it is totally dry, right? It is totally dry, or in other words I can say unsaturated. Okay, now at time 5 minutes we have given 250 centimeter cube of water, and now what happened, soil in this region start getting the moisture, start holding the moisture now, moisture in the voids. So after certain period of time, this soil will be getting completely saturated, right? And after that it is not going to hold water anymore, because it is having a specific amount of volume in the in what volume in the voids. Okay, so it could only hold certain amount of water. So after that definitely infiltration is going to be constant. So it is asking about the constant infiltration value at which soil is completely saturated. So can anyone tell me the approach that how we can proceed? Note it down that we have also provided infiltrometer ring diameter. It is given as 20 centimeter. Ashish, can you tell me the approach?
So we
see, it is in journal you can have some idea that yes, like in terms of unit I am just talking. Okay, so let's see that we have volume in units of centimeter cube. And what we are required to find out, we need unit in terms of centimeter per hour, right? So definitely if we divide this volume by area of infiltrometer, we can have what infiltration depth we can get now, right? So we could be having idea that yes, infiltration depth is this much. And now if I divide infiltration depth with respect to time, can I get the unit like this, centimeter per hour? Depth will be what unit? Depth will be unit of centimeter, right? And time, we already have time in minutes. We can convert it in hours, right?
Hour. Yes.
So we can finally achieve this centimeter per hour, right? So you got the approach that how we are going to solve this problem?
Yes.
So for your information, I've just briefly described the approach. Now you need to solve like at least for 5 minutes you have to compute the constant infiltration rate. So look at this table, okay? Don't directly go with the answer, okay? This is only for your reference at the last. So now see, we are provided with the details which are mentioned in column 1, and then at column 4. Ashish, any idea? Like you are getting that what is happening in this table?
Yes.
Okay. Now for 5 minutes, what?
Yeah, 5.
Yes. So firstly, what we are doing, we are converting this 5 minutes into hours, right? Then we are also computing the incremental time, because whatever the values are there, they are cumulatively mentioned in the column 1, right? Like you can assume that once the water is being added in the infiltrometer, we have a stopwatch, okay, and we have just started taking the readings. So how much water was infiltrated at 5 minutes, it will be getting accumulated when we are measuring at 10 minutes, right? If I say for 5 minutes 2 centimeter depth of water have been infiltrated, but after 10 what you will be getting? You will be getting like 5 centimeter have been infiltrated. So it is cumulatively mentioned here. So we have to find out the incremental time, that yes, for delta H time, how much infiltration have been occurred in the region, or maybe in the layers, soil layers, right? So Ashish, try to get the values, even everyone try to get the values.
Yeah, I got the values for the first one. It's correct.
Okay,
0.796 and 9.5.
so how you are getting this area of infiltrometer?
Pi by 4d square.
Good. So pi by 4 d square. So pi by 4 into what was the dia?
I calculate 600. I think just a minute. 3.14 divided
No, no, no.
by 4.
I'm just asking about the dia. That what was the magnitude? It's a
It's
20
given
20, 20,
centimeter.
20 centimeter.
Right. It was 20 centimeter. So we will be getting approximately 314 centimeter square, right? You can calculate for your reference. Now, once we compute the area of infiltrometer, we are just dividing the cumulative volume of water added with respect to area of infiltrometer. So volume upon area, and try to get this value. Are you getting this? If not, then I can compute by myself. Ashish, you got the answer, right? Let me know whether like I can see for myself. Wait a minute. Okay. Bala Murugan is replying. That's good. Okay, Manikanta is also replying. No transpiration, good. Good. That's good.
So,
Okay.
Got it, sir. Got the value. Thank you.
Then what about the incremental depth? Now, how we can get the incremental depth value? So what we are doing? We are subtracting 1 by 2, right? Ashish?
Got it.
Got it?
Yeah.
And then after that, we are computing the infiltration rate. So compute that value. So this is what? This is, if I am talking about the infiltration rate, so it is just a ratio of infiltration depth which was found after increment divided by incremental time. So tell me whether you are getting this value.
0.637 divided by 0.108. I'll be specific. 0.167. 0.083. So it's 0.084.
So it will be simply a division of 0.796 with
7.5, 7.6 I'm getting. 7.6, yes, correct. 7.5.
Second one.
Yes.
Okay. So in similar fashion, if you are computing for other time as well, so you can observe the change.
Yeah,
Ashish, can you tell me the change?
yeah. Infiltration rate become constant.
Yes, right. So now, for if I say that yes, this is just a subsurface zone and soil layers are here. Soil layers are here. Okay. So this is delta. If I talk about incremental depth, so if I am saying delta f, okay. So delta f value we are computing here. Delta f we have now, at the same time delta h we are knowing. Got it, Ashish? And we are computing the delta f by delta h. So this is a rate, incremental rate, this infiltration rate. Got it? Now,
Mhm.
when we are about to touch 150 minutes and 180 minutes at the last, we are observing that infiltration rate is now constant, because entire soil voids are now saturated, completely saturated. They can't store more water now. Am I right or no?
Mhm.
Can soil voids store water beyond their capacity?
No.
No. Yes. That I want to mention that after 150 minutes and 180 minutes, you can say infiltration rate is constant now. Anyone is trying to join? Okay. Okay, Ashish. Shall I move ahead?
Mhm.
Yes.
Okay. So
One
now,
question. I can you go to the back slide?
right, right.
Yeah, from the data we can see the initially the at the infiltration rate can vary from high or low, but at the end infiltration rate become constant.
Yes, right. So basically, whenever we are, I'm just talking about infiltration rate. So there are properties which are related to the soil texture. If I'm just saying that yes, infiltration rate is high, infiltration rate is high at 5 minute as compared to 10 minute, right? So definitely there could be possibility that soil texture may be vary. You can assume in the
Hmm.
first layer it may be a sand, right? Or and if we are going deeper, there may be a mixture of sand and clay as well, right? So what is happening here? If clay is here, then it will try to hold the water, and now infiltration is getting lower now. It is not passing uh, with the rate that was initially found in case of sand. Got it?
Hmm.
If you have doubt, you can still discuss.
Yeah, yeah, I got it. But at the end, when infiltration rate further become constant, or it will decrease further over the passage of time.
Uh, yes. So at the passage of time, you can see it is nearly. I can say it is 3 hours, right?
Hmm.
So like whatever the water which was accumulated, which we have provided, which we have given in the infiltrometer, it has finally reached to the depth. Like I can say that is what we are saying, that is that is a front, right? At the front it finally reaches. So at that point, infiltration depth, it is not varying now, right? With the time it is not varying at all.
Hmm.
But we can't just say that yes, uh, because of the texture only this lower values of infiltration we are getting. Okay, there may be some other parameters as well related to moisture. Maybe initially there may be some kind of moisture already present in that layer. Maybe there may be a chance. Okay. Yes.
So I can say that if the soil is completely saturated, there is no infiltration, then the infiltration rate is zero.
Yes, right. If it is
Okay.
completely saturated, then definitely infiltration will not be happening in the region, and you will
Okay.
be getting infiltration rate as zero.
Okay, got it, got it.
Similar to the previous question, we again have infiltrometer experiment data, time versus cumulative volume of water added. Now, in the previous case, question was related to constant infiltration rate, that at what time we are getting constant infiltration rate value. Now it is asking about average rate of infiltration for initial 30 minutes. So for initial 30 minutes is what? That is 0 to 30 minutes, right?
Hmm.
Now it is asking about the cumulative value, cumulative rate of infiltration. Got it?
Hmm.
Because it is asking for the initial 30 minutes. So initial 30 minutes is what? That is 0 to 30 minutes, right? So
Hmm.
we have to compute cumulative rate of infiltration here. So we don't need to find out incremental values now. Got it? In the earlier case, we were asked to find out the constant rate of infiltration. So what we did, we tried to divide the accumulated or cumulative values in different time frame, and then we have
Hmm.
computed the data. But now we have to compute directly. So for this, we already have time, we have cumulative volume of water added. So I will be adding writing like this. So
Hmm.
0, 5, 10. So they are already in minutes. So if we are about to compute in hour, centimeter per hour, so what we have to do? 5 by 60 and 10 by 60, right?
Hmm.
So it will be giving us units in hours, right? And at the same time, we have 250 centimeter cube of water which was added in 5 minutes. After that, 450 centimeter cube. Now the similar process will be followed, right? So what we have to compute? What we need to
We
compute?
depth.
Yes, definitely we are about to compute the infiltration depth. But how we will get? We are having the volume and we are targeting the depth value. So depth will
Yeah.
be in
So
unit of centimeter. So how will you approach?
the same formula we divide the volume by area.
Area, yes, that is the thing. So area you have to compute. So area will be what? That is pi by 4 into d square, right? So tell me what is the value? It will be same only.
Three same only
Okay,
314 centimeter square
314 you are getting. Okay, now tell me the depth value. So depth will be what? 250,
divided by 314.
314. Now tell me the value.
The value is 0.796.
0.796. Good. So it will be in centimeters.
Yeah.
Now you got the infiltration depth. Now you also know that this infiltration depth was achieved at 5 minutes, right?
Hmm.
So 5 minutes you have already computed, 5 by 60. Now you have to divide this. 0.796 divided by this converted value, this in hours. So divide it and tell me the final value.
The value is 0.0026. 0.0026. Yep. Yeah, correct.
Okay, okay. 0.00.
26 centimeter per hour.
Okay, let me see. How come? Okay, wait. How come 12.61?
5 divided by 60 is 0.03.
Okay,
Just a
okay.
minute. 0.796 divided by 0.083. No, it's 9.59. Sorry.
Balamurugan, whenever we you might have gone through some of the empirical equations, right? So what they have done, like for an example, if I take Horton's equation, right? So you might have come up with the parameter. There is one parameter called kt, e to the power kt. Ashish, do you remember this Horton's equation?
So my answer is wrong. That is 9.552. Sorry.
Okay, Manikanta is getting how much? Okay, 5.1. Balamurugan, I am just saying that there is parameter k which is just associating the properties which are not known to us at that time. Okay, those could be soil texture, soil properties, maybe soil dense like how the soil is behaving when the water is passing through that. Clay soil may be there, sandy soil may be there, maybe there may be a possibility that yes, of course, water may be present like at the beginning. There could be a possibility. So before starting the infiltration test, what we did, firstly we have to select the site, a specific site also. That is also one of the like a key challenge when we are performing the experiment in the field. So that site should not be having any kind of external supply of water. So we could have some good idea. Like if I say that I am just performing the infiltration test near the canal, can you do this? Like definitely there will be a external passage of water. Water is maybe seeping from the canal also. So you may not be getting that much accurate result. So definitely whatever the variations are coming, it is because of the properties which is not known to us. Okay, Ashish, how much result you are getting?
9.5 centimeter per hour.
Okay,
Yes.
yes, you are getting the value. Yes, right. So this is 9.554. I guess Manikanta was answering something 5 point approx. I guess he is getting final answer, right? Manikanta, are you getting final answer? This is your final answer because okay. Ashish, let me know if he is replying. Okay, for time being, I'm moving. Okay, Ashish, you got this value, right? 9.554.
Yes.
Okay. Ma'am, are you getting the answer? Okay. Ma'am, you have also raised a question. Can you tell me?
I'm just working. I didn't finish, but I that's why I didn't give the answer.
Okay, okay, yeah.
I worked, but I just got stuck up in between, so it was delayed. I'm working now.
Good. No issue. Ashish,
Yes.
try to get the value you can compute for 15 minutes as well. Like are you getting this because whatever the calculations are here, they are
Hmm.
from my side, right? There may be a
Sure.
possibility
Sure.
that you are getting some other values.
Okay. Just a minute. I'll check it. 1250 or
So we are getting cumulative infiltration based on after volume divided by area.
yeah, 9.936. I'm getting.
Okay, that's good. So after you get the cumulative infiltration for 30 minutes, you can have some idea that yes, average infiltration rate for 30 minutes from starting 0 to 30, because whatever the values we have, this is in incremental only. They are
Hmm.
getting in the form of increment. So final answer will be 5.732 centimeter per hour. from the name itself you can have idea that it is asking about average infiltration rate. Okay, yes, okay, 5.732. Good. Now there is one more question related to infiltrometer test. Here firstly see the data which have been provided. So here again we have the diameter of infiltrometer. How much it is? It is 30 centimeter. Ashish, try to solve this numerical parallelly with me, okay? Yeah. Now we also have data for initial infiltration rate. So this is, do you remember this initial infiltration rate, F naught? Do you have any idea? There is one more word that is there, constant infiltration rate, that is FC.
Yes.
So F naught they have provided, F naught they are asking. Now at the same time they have provided the field data, time versus infiltration rate. Now can you tell me from the graph, can you tell me what could be the graph, we will obtain if we plot this, whether it will be a rising, whether it will be like in relation to time, infiltration rate is decreasing or it is rising?
Decreasing.
It will decrease.
Yes, right. So do you remember this graph?
Yes.
What we call?
Infiltration curve.
Yes, if we have
We say mass curve.
no, it's an infiltration rate curve. I'm just plotting.
Infiltration rate curve.
Right.
Yes, I got it.
So I'm just plotting here. So you may be knowing Horton's infiltration rate curve, rating curve. What is it? Ft equals what? F naught plus
Yeah, Ft is equal to yeah, correct.
e to the power minus kt. Ashish, you were asking about the variation now in the previous question. So because of this parameter, those fluctuations are arising. This K value.
Okay, hydraulic conductivity due to.
No. This is not K. This is not a hydraulic conductivity. This is a parameter which is correlating the field conditions, which are ignoring right now, because we are getting the values which are directly obtained when we are using the stopwatch. We are changing the water label in the infiltrometer. So we are having only the Ft, F naught, Fc and even T, but we are not knowing the value K. This is relating the soil condition, which we are not knowing right now. There, if I say there could be one more reason, that if trees are nearby that location, then also there may be some change in infiltration rate. It could be possible. Okay. Now, can you tell me the constant infiltration rate value FC and
3.1?
Yes. After 75 to 110 minutes, we are getting value of 3.1 centimeter per hour. This is getting constant now, right? So we already got the value 3.1. What they want to know? They want to know the initial infiltration rate. So initial infiltration rate will be what? This is F naught, right? They want us to compute F naught. And what data we have? we only have FC value and we have this graph. Okay, graph in the sense this time versus infiltration rate. Got it? So from this picture you can see, if you are talking about the Horton's empirical equation for computing the infiltration rate, then this equation you may be knowing, Ft, which is varying with the Fc, F naught, e to the power minus Kt, right? Now if we have the data of Ft versus T, we can come up with that graph like this. And how we can do this? So they have just substituted, they have made some arrangements, and we will finally plotting ln Ft minus Fc versus T. Got it? So Fc we already got the value Fc, we know that, and Ft value is what? That is given in the table. Got it, Ashish?
Could you please explain it again?
Yes. Okay. I'm just saying that we want to find out F naught, right? And we already got the value Fc. Got it? Also, we have infiltration rate with which is varying with the time. Like this is Ft. It is varying with the time. It is not constant, but it is varying with the time. So it is basically dependent on time t, right? Now, if we want to quantify F naught, can we do directly? Like if we have F of T minus F of C, which is written here, you can see, which is written here. Okay, now because of E value, because of the E, that is exponent, we are not able to solve directly. We are not able to get this F naught directly, because this E, this exponent value will be a challenging task, because we also don't know the K value now, right? We don't have idea about K. So how you will do it? So in order to make it easy, what arrangements have been made is that we are taking F naught, this Fc to the left side and the remaining term in the right side, and then again we are taking the ln, that is log value, okay, log base to the E. Now we are getting this value, and at the last you can see the relation, and this relation is what? This relation is in the form of y equal to mx plus c. Got it? This ln Ft minus c we can write in y axis, and at the same time this time t we can write it in x axis. And what is remaining here? Ln F naught minus Fc. This is nothing but intercept form, that is we are saying that C. And now how we can get the K value? Can we get the K value? If we have equation like this, how we can get the K value? Ashish?
Plot the points and get the y-intercept.
Yes, right. But I am just asking about K. So K will be just a slope. Okay.
Slope M.
Yes.
Oh, slope. Sorry. Slope.
Right.
Slope. Sorry.
So it will be a slope only. So once we plot this graph, after getting this plot, we could have understanding that yes, there is intercept like C, and at the same time there will be having a slope of this line, this straight line, fitting line. We will be fitting this entire data with certain kind of this straight line, or we can say what could be the possible curve we can use. But for time being, whatever the data you will be getting, it is totally a linear one. So you will be getting direct data from here. So slope will be slope can be computed, and we can get the K value directly. Now Ashish, you can see we already have the Fc value 3.1, and now we are about to find out ln Ft minus Fc versus time. So how we are approaching here? So table is here. Now you have to do you have Kelsey right now,
Yes.
yes, because I just want you to compute ln value, because that is important. If you are getting that value, then definitely if it is matches with you, then whatever the data it is mentioned here, computation have been mentioned, it is correct. Got it? So what we have to do, we have to target ln ft minus fc. So we have to compute value for every time step. So do it. So we have data, direct data from the field, that is infiltration data, and we also have data time. Now what we are doing, we are converting it. Firstly we are converting time in hours, because our data, that is constant infiltration rate, it is also in centimeter per hour. So firstly we will convert it into hours. That will be easy for us in calculation. And then you have to compute ft minus fc first, and then take a log of that.
FC is 3.1. Just 21 minus 3.1 is 17.9.
That's good. Yeah, good. And tell me the value of ln.
Value is correct. 2.885. Yeah, I have checked it.
That's good. And also try to check the value for 60, 75 and 110 also. That
So
why
let's.
I have just ignored these values, like what you are getting, I just want to know.
So log 0. Yeah.
It was
Okay, table is matched for me. Good, Balamurgan.
Yeah.
uh, Ma'am, are you having any question right now?
No, I'm also working. I got it. I'm working.
Okay, that's good.
I understood your explanation.
Yeah.
Yeah, for 75, 3.1 is okay. We minus 3.1 from 3.1, value is 0. FT minus FC is 0.
Okay, ft minus fc is 0. Now if we are getting the 0 value, then definitely ln of taking 0, it is not defined at all, right?
Not defined error.
Yes. So I just leave this space blank. Okay.
Uh-huh.
Now what is our next task? What is our next task after this table? What is our next task?
Okay, the task is. We have to calculate the initial infiltration rate.
Firstly, tell me that what we are trying to achieve right now. What we are targeting. What was the missing thing? What we were not having at that time. Okay. Firstly, tell me.
F naught, F naught.
Wait a minute. I'm not getting that. Okay. Okay. I'm just saying that you were having FC at initial, you were having that data. You were having a T value also.
Yes.
You were also having FT value also at that time. What left? F naught you don't have the
Yes.
value, right? And
Yes,
at the
yes.
same time K value is not here with you. So now we are plotting a graph in order to get two values. Firstly F naught as well as K value, right? Because do you think from a single equation two unknown parameters can be computed?
No.
We already have this equation only, right?
Yes.
For solving two unknowns, we at least need two equations. But at present, we only have one equation, and we can't compute K, F naught in parallel. So what we come up with plotting a graph. So now, whatever the things we are doing, it is for plotting the graph. Plot between what? Plot between what?
FT minus FC.
This one.
Log FT.
ln,
Yeah, yeah.
yes, ln ft minus fc with time. This time.
Time.
So
Yes.
now we are about to plot the graph between them. Ma'am, are you getting? Okay, Ashish. Now this is the graph. Maybe whenever you are solving this problem, like if it is a written examination, then definitely you will be provided with the graph also. And what you have to do is that you are providing the ln ft minus fc, which is varying with the time. Got it? And see that these points are mainly like it is fitted best in a straight line. Okay, if I will be getting points in this manner, in this fashion, okay, then definitely there could be a possibility of curve. But this time these points are best fitted with the straight line. So just I draw a straight line here. Okay, and now once I get the straight line, I can have intercept value, right? And how much is the intercept? How much is the intercept? So intercept value is up to this much. You can see it is not touching the exact 3 value, right? Ashish?
Yes, yes.
Wait a minute. Yes. I'm just saying that yes, this point is not exactly touching 3. It is just touching nearly to 2 point something. 2 point something, right? 2 point, I guess you can say 8 or something. Got it? Ashish?
Yes, yes, somewhere.
Yeah, right. So we already got the C value. Now we were looking this equation, y equals mx plus c. Now we got the value c, that is nearly 2.8. Now we want to know m. So m is just a slope. M is just a slope value. So for computing this slope value, you can take these 2 points and try to compute the h value as well as the b value. I guess from this graph you could be able to figure out delta, this one, delta h. So delta h will be approximately, it will be 1, right?
Yeah, 1.
And what about the b value? So b will be in round figure, I can say it will be approximately how much?
1 plus 0.5. So
You
half.
can say if it is
1.
like
0.25.
0.25. No, I don't think it would be 0.25. It will be more than
1.
0.5. Or
1.
maybe
Yeah.
no, not more than 0.5. Maybe
Sorry. Yeah.
mm,
Yeah, it's more than approx.
0.3 I can say, or maybe if it is like that, if it is coming 1 upon maybe 0.5, if I'm say, taking as 0.5, then how much it is coming? It is coming around 2, right?
Yeah.
But from the equation, this whatever the graph you are seeing, this is generated from the Excel. Okay, I have directly plotted
Okay.
from the Excel. But if you are having direct graph, you can have better idea, you can directly compute. So the task is what, that you have to get the value of h, that is a vertical value between the 2 points. Firstly you have to select the 2 points. Okay, try to select the 2 points and then you have to compute delta h first, like that is the difference between the elevation, like elevation, or I can say difference in the y axis, what is there. So you have to compute this delta H. What is M basically? M is basically a tan theta, right? Tan theta is what? That is delta H by delta of X. So here from this I can it is approximately I am getting that one unit is there, and then delta X I am getting approximately maybe 0.5 or something. It will be less than only, because it is here values are nearly 3.7. okay. And you can also see that this graph is not rising, it is not going upward, right? It is going downward. So because of the downward direction we are getting a slope value as minus. Okay.
Okay.
So in round figure I am getting -2 here after looking directly at the graph, but yes, from the Excel the correct value is -3.70. You can also plot these values, you can directly get it from your Excel also. And now also you can see after fitting this straight line with these points, I was getting this R square value. Basically it is representing that how much fit have been observed. So it is saying that 99% the data have been fitted in this straight line. It is falling in the straight line. Okay. So this is this equation we directly got from the Excel. We directly got this y is equal to -3.7x plus 2.768 something. Now what we are doing? Tell me the value of y. What is the parameter we have considered for the y? So y for this parameter is this na, ln fc ft minus fc. Ashish?
Y is equal to ln ft minus fc.
These are the variables only, na?
Sure.
For x-axis, what is your variable? Your variable is time. Right? So for x you will be writing t, and for y what you will be writing? You will be writing ln
ft minus
fc. Yes, that is the thing I am saying. Now from this, using this equation, you can see here directly from the graph after fitting the best straight line, this is y value, y equal to mx plus c. It is directly written here. Any confusion here? Any confusion here?
No.
Okay. So y value we have directly achieved here, and at the same time k value also got it, because m is k. M is nothing, it is a k value. M is a k value, right? Ashish, any confusion it is going on?
No.
Now we have y value, right? And which is dependent on x, that is a time. So now in order to get the y value, okay, for time t equal to 0 we can quantify exactly that. Yes, at time t equal to 0 what could be the parameter here? What could be the parameter here? So we are keeping we are keeping t equal to 0 in this entire equation. Now what you will be get? You will be getting this value as 0 entirely. It will be coming 0, right? I am just putting t equal to 0 here in this equation. Will you get this?
Yes.
Got it?
Got it.
Now this is ln. Ln is what? That is log of e, log of base e. So what you have to do, if you want to take out f naught minus fc, you have to take e value to the right hand side. So e to the power 2.7685. It will be like this. This is a part of calculation, right? So try to compute this value, e to the power 2.7685.
Okay.
If you still have any doubt, you can discuss, because it is a part of computation. I can tell you if it is still confusing.
Yeah, 15.93 is correct.
That good. So now you got what? You got the value of f naught minus fc directly, that is 15.93. Now what was our target? Our target was to quantify the initial infiltration rate. Ashish, can you tell me why I put here t equal to 0? Why not other values?
Because we need to calculate at initial rate.
Yes, and initial will be at t equal to 0 only, na, right?
Zero,
Not
zero.
exactly 0, but
Yes,
yes, of
yes.
course, 1 second or 2 second it will be counted nearly as 0. So that's why I put like I considered boundary condition for f naught as t equal to 0. Okay. Now putting the FC value, you can directly get that how much initial infiltration rate was here. So 19.03 centimeter per hour. And similarly, you can get the initial infiltration rate finally. At the last, you can also write Horton's equation for this test is. Now, what is the benefit of writing Horton's equation in journal? Benefit of this is now you can put time value like maybe 5 minutes or maybe 10 minutes. You can have direct value of FT because your parameters are known now. What is minus 3.007? It is K only. It is KT. Ashish, this is the equation of form FT equals what? FC plus? Ashish, tell me.
FC plus F naught minus FC into e power minus KT.
Okay. So am I writing right or wrong? FT is equal to FC, that is a constant rate of infiltration. Then difference of both of them, like FC minus this one, F naught minus FC and e to the power minus of KT. I am writing like this. And now you can put the values and you can directly get Horton's equation in journal. Got it? And what is Horton's equation? Basically, it is an empirical model, you can say. Okay. Every model is just based on a kind of, like if I am talking about empirical equation, then it is associated to a model like y equal to mx. Now, what is there? Actually, you have to provide certain kind of input and you are getting output for that input. Got it? So Horton's equation is a kind of model where we are providing the time after knowing the field condition, like field condition parameters, and then we are computing the infiltration rate in that region. Now again the problem is related to infiltrometer only, but here the question what they are asking to determine the parameters. Now tell me the parameters, just I discussed. What are the parameters? Horton's infiltration model. What are those parameters? Do you remember the equation?
Yes.
So that is FT equals FC plus
F naught minus FC e to the power minus KT.
Now what are the parameters? Parameters are which are the unknown values. Those are the parameters, right?
Yes,
For this
yes.
question, they have provided what? You already have time value, you already have FT variation. So you got the FT, now you got the T value. Now what are the unknowns? So your unknowns are K value. Now another one is
Yes.
what? F naught. This
F
is
naught.
this is an unknown parameter. Now at the same time FC is also an unknown parameter. But from this data, from this given data that is in the table, you can directly compute the FC. You can have some
Yes.
idea.
1.
1. Ma'am, are you agree with this? Sorry.
Yeah, I understood. It's 1.
Right.
Got it.
Okay, so you got the FC value now. Now, what is the process to compute K and F naught? What is the process to process or maybe approach we can compute K and F naught?
Similar process we have to follow
Yes,
the
right.
slope
Taking
diagram.
natural logarithm. And,
Yeah, yes, right. So similar process. In the earlier case, what we have followed, we have to follow the same. The thing is, here this entire problem is more easier if we got direct parameters, like if we have k value, f naught and fc, because here mainly our calculation may get wrong if we don't pay attention while plotting in the graph, that is ln f naught minus fc versus time. So in that case only there could be a possibility. Now this is just for your information that yes, here in this case equation was whatever the points were there, we were getting the equation y equals minus 3.1x plus 2.344. Now tell me the k value from this equation. What is k value?
So k value.
Don't get confused. Y equals mx plus c, and I am just continuously saying that m is representing a k parameter.
Yeah. 3.1 is the k
always
value.
3.1.
Yes, minus 3.1. This you are right. So it is a k value, right? Maybe magnitude won't be considered because k is only a positive. In terms of magnitude, we will be considering 3.1. But whenever we are expressing in the Horton's model, so we have to take minus 3.1. For the remaining part, like c, again the same thing is happening. This entire constant, whatever we are getting, it is as just a c value, and we are trying to keep the value. If we want to compute c value here, we are putting x equal to 0 again, and we are simply getting the value, you can see 2.35, and after computing that you can see f naught is 11.49. now the model is ready. Now ft is in the form of kt. Model is ready now. Any confusion in this? Now there is one more question related to average infiltration capacity. What are the data? We will be solve it quickly, okay? So focus on the data. So we have area of the catchment, that is 600 hectare. So in meter square, how much it is?
610 to the power 4.
Yes, that's good. So it will be a meter square. Now what they have additionally given, rainfall intensity they have given. So I am writing it as I. So IR they have given, it is 2 centimeter per hour, and it is continuously falling for 8 hours. So I am writing it as at the rate 8 hour. Now one more thing they have provided, that is surface runoff. So surface runoff I am writing it as R. So it is given 0.6 million meter cube, and now they are asking for computing the average infiltration capacity. I can write it as F average, okay, and we want to compute this. Now how you can do this? Any approach?
Yeah, we need to minus the runoff from the water stored.
Exactly. So whatever the input, whatever the rainfall it is falling here, we will be subtracting the rainfall depth with runoff depth. What I am saying, keep in mind that I am talking about runoff depth, okay, and at the same time this rainfall depth, okay. So firstly we have to compute rainfall depth, and then we will subtract it by runoff depth. Now tell me, what will be the runoff this rainfall depth? If we have the intensity known, and we also know that how much time this rainfall occurred in the region, so what will be the total rainfall?
We need to multiply intensity with the time.
Yes, so it will be 16 centimeter, right?
That's correct.
Ma'am, is it clear?
Yes, clear.
Okay.
Yes,
Good.
sir. Thank you.
So we directly got the value 16 centimeter now. Now, what about the runoff depth? How we can compute the runoff depth? So runoff depth, you can see in terms of unit, you can see it is in form of volume, right?
We divided it by area.
V divided by area, that's simple. And what is the volume? Volume, you have to open it because it is in a million meter cube. So 0.6 into 10 to the power 6, right?
Yes.
It is will be in meter cube, and now you are dividing by 600 into 10 to the power 4 meter square, right?
Mm-hmm.
Now tell me what is the value you are getting.
0.6 into 1 minute. 6 into 100 by 600. 0.1.
0.1, sir.
Okay,
Has
0.1.
0. Yeah, correct. Point 0.1.
Okay,
0.1.
so 0.1 it will be in meters, but we have to convert it into centimeter because
So,
rainfall we got in 60 centimeter.
mm,
So how much it is?
10 centimeter.
That's good. 10 centimeter.
10 cent.
So what will be the infiltration? If
6 centimeter.
yes, 16 centimeter of rainfall occurred in the region, and
Mm.
simultaneously 10 centimeter have been like flow away as
Yeah,
in the
yeah.
form of runout. Now how much it have been, how much amount of water have been infiltrated? So it is 6 centimeter.
Mhm.
Now average infiltration capacity it is asking, so it is in the form of rate. So within 8 within
So,
8 hours
yeah.
6 centimeter of rainfall I can say, okay, infiltrated with beneath the ground, okay.
Mhm.
So tell me the infiltration rate will be what?
Point,
Centimeter per hour.
0.75 centimeter per hour.
Ah, that's good. Yes, this is a quick one. Good, nice try. So see the answer, you got that, okay.
Mhm.
It was easier or not?
Yeah, it's easy. No
Okay,
issue.
now come to the next question again. So again the Horton's infiltration equation question is related to Horton infiltration equation only. So
Hmm.
firstly tell me the equation again. It should be learned by from your side now.
Yeah, yeah, yeah.
Tell me.
Is equal to Ft is equal to Fc plus F naught minus Fc e to the
E to the.
power minus kt.
Yeah, that's good. Brilliant. Okay.
Yes.
So now see what are the parameters they have given in the question itself. So what are the parameters? So they have given initial infiltration capacity. What is this?
F naught.
Eh,
Yes,
Yeah, F
right.
naught is equal
F
to
naught is
10.
given. F naught is given and it is 10 mm per hour, right? And then if I talk about final infiltration capacity, so this is
FC.
FC, right?
Hmm.
And
Yes.
how much it is? It is
5
5
mm
mm.
per.
5 millimeter per
5
hour.
mm per hour.
Yes, that's good, ma'am. Then again, exponential decay constant is given. That is a K value.
Hmm.
Am I right?
Yes.
Hmm.
And you can see the unit also. It is 0.5 per hour. It is there
Hmm.
like this. Now, whatever the unknown parameters we were looking while we are modeling the Horton infiltration curve, this empirical approach. So we already got the unknown values. F naught, FC, K is known. Now what is it is asking? It is asking to compute the total infiltration depth for a uniform storm of duration 8 hours. Ashish,
Hmm.
tell me what is FT? Is it total infiltration? FT is
No, no,
total
no.
infiltration?
Infiltration per unit time.
Yes, good. It is infiltration per unit time. So what we have to do in order to compute this FT, total infiltration. So you might have gone through lectures that if we want to compute total infiltration, that is FT, we have to just integrate. We
Summation
have
of
to, yes,
infiltration rate.
exactly. So f of t we have to integrate, and
0
from
to
where
t.
to where? T equal to maybe t1 to t equal to somewhat t2 value.
Hmm.
So we can achieve direct value of total infiltration.
Hmm.
Got it? Now you already have this ft value, right? You already have this ft value, right?
Yeah,
ft,
we need
you know na,
to.
from the Horton's equation, you know
Yes, yes,
what
yes.
is the
Got
form.
it.
This form will be like ft equal to, say, tell me what is the fc value.
Uh, FT is
No,
FC
5,
plus F.
yes, 5, right. 5
Okay.
plus then f naught minus
10,
fc.
10 minus 5, again 5.
Again 5, right? Then e to the power minus k. K is what? 0.5.
Yeah.
And t
Minus
we don't know.
0.5.
Yes, right. Now we have to put this equation here and we have to integrate it, and then we have to compute the total infiltration value. So I hope you all will be familiar with the integration concept.
Yes.
Okay,
Yes.
good. So I want you to compute this value, because I don't think there could be a direct answer for this question. I don't think so. Yes, there is no direct question, but yes, what are the concept is associated to this? I just mentioned here. So we can compute here. Okay, so compute it. Ashish, tell me. I am writing here. Ft t equals, what will be the T1? What will be the T1 value? Can you tell me? Total infiltration depth, it is asking for a uniform storm of duration 8 hours.
So T is equal to 0. T1
T1
is equal
0.
to 0.
Exactly,
Yeah.
yes ma'am. So T equal to 0 and then it will reach up to 8 hours.
8 hours.
Then now we have Ft value. Tell me Ft value. 5 plus 5 e to the power minus how much? It was 0.5 I guess. 0.
0.5.
Yes.
0.5. Yeah.
Okay. So 0.5 into T. And now this one. Now tell me the integration of, like, I'm just separating this bracket. I'm opening this bracket again. Let's see, t equals 0, t equals 8r. Then this will be 5 into dt plus t equals 0 to t equals 8r. And then again we are having 5 e to the power minus 0.5 into t. 5 is constant, we can take it out here. There is no problem, and we have to integrate this alone with respect to dt. So what will be the value of this? It will be 5t, right? Do you agree with me?
Is 5T.
Right. Okay, that's good, ma'am. Now tell me the value of this. So 5 will be out here. What is the integration of e to the power x? If there is some kind of e to the power x, or maybe I can say e to the power ax. Integration of e to the power ax with respect to dx. Do you know?
Sir, e to the power x by a.
Yes, it by upon a, right? Am I right?
Yes, sir.
Yes.
Yes,
Okay.
Yes,
yes.
sir.
So for here we will write it here 0.5 into t upon minus 0.5. I'm
Into
taking
T.
in bracket. Okay. What is left? I'm leaving anything, or is it clear? Okay.
Yes,
Limits.
sir.
It will be t again, or t square. What will be there? We have to take the integration of this partner, right? Again it is left. So it will be 0.5. Manikanta, tell me. Manikanta, are you here? Ashish, any idea? Hello.
No.
No idea?
No.
Okay. So time being, yes, 5 into e to the power, this one is right. Then again, I guess this is sufficient. There is no need of adding anything else. Okay. Now you have to
Yes, sir.
compute you have to solve this value, and you can get the final capital of ft. Okay. 5 8 minus 0 plus 5 upon bracket, in the sense 5 0.5, and then you have to solve minus 0.5 into t. So I guess this t will be varying, right? 8 minus 0.
Myths again.
Yeah. So whatever the computation finally you will be getting, that will be the answer. I just want to add that this is just for your information, like how we have to approach. If we already know the parameters, then how we have to approach in order to quantify the total infiltration. Because till now what we are finding the infiltration rate. We are continuously uh, trying to find out rate with respect to time. But if we are about to find out total infiltration, then how we can do it? So we have to take the integral of infiltration rate. Got it?
Yes, got it. Thank you.
Yeah. So this is for the today's session. Yes. Now the remaining, there are certain questions which are still left for this. Like there are some empirical approaches like related to green Ampt. You may be facing some numericals on that. So in the next session I will be covering some numericals on the green Ampt theory. In parallel I will also take some numericals on Phillips equation as well. Okay. Yes. So we will
Okay,
meet in the
thank
next
you.
session.
Sir, I have a question.
Okay,
Yeah,
thank you. Thank
Manikanta,
you very much.
if you are having
Yes, sir.
any question, you can.
Sir, for this question, the answer around 50, but in option there is no 50.
What?
Sir, the answer goes around 50 mm.
You are saying the answer, right?
Yes, sir, yes, sir. In the options, but there is no option 50. 50
Okay,
mm
you okay? Option is not there, right?
in the option.
Okay. Let me. Okay. What is your answer?
50 mm, sir.
50 mm. Okay. Don't worry, Manikanta. I will check it out. Okay, and in the next session we can discuss it. Okay. I will
Okay,
confirm you.
sir.
Okay. Don't worry.
Just a small
Okay, sir. Thank you.
representation. The same, I had a problem in assignment, previous assignment. I had
Yeah.
given hexadecanol or cetyl alcohol.
Right.
It just took it as wrong. I think because it is system generated, it just takes one string. Is it right? For an element which controls evaporation, the
Yes.
answer I had given the chemical name hexadecanol or cetyl alcohol. It made it wrong. And we had discussed a problem based on pan coefficient.
Right.
So it ranges from zero 0.7 to zero 0.8. So
Right.
when it's not given, we can assume.
Yeah. Of course.
Substituting 0.7, we had a lower value. That is
Okay.
also taken as mistake and it takes the upper value. So both were wrong for me in an assignment. This is just a representation.
Okay.
We feel a bit disappointed.
Okay. Means you are submitting the assignments, but you assume some values, but they are not considering.
Yeah. That
Okay.
problem you discussed in class. So zero 0.7
Right.
pan coefficient can be taken ranging from zero 0.7 to zero 0.8.
Right.
So I used 0.7 and got 28,000 or something. That answer was taken wrong and the upper limit was taken correct. Similarly, cetyl alcohol has that chemical name hexadecanol. I had given both, it said wrong. So I think certain
Okay.
things I do not know how to represent, or because it is system generated,
Yeah. So
it fails.
definitely, thank you for your response. Definitely, I will raise this
Kindly
queries.
represent. I mean,
Yeah.
it's not a big thing, but
No.
still please represent.
Yeah. Of course, I
Thank you.
will.
Thank you.
Yeah. Sure. Okay, Bala Murugan, you replied. I guess everything good. Nice to see you participating. Maybe in the next session we will be having more questions. Manual graph will give different intercept. Okay, that's good. Yeah, right. Because it depends on person to person. That's good, Bala Murugan. You are replying. Okay. So I'm just stopping now here. Any question from your side, Ashish?
No question from
Manikanta?
my side.
No question.
Okay. So, ma'am, I'm just now stopping the session. Okay.
Okay, thank you
Okay,
very much for your
thank you
time.
very
Thank you.
much.
Okay.
It was nice. Thank you.
Thank you, sir.
Thank you. Bye.